Uh, okay, so it's a pleasure now to have with us John McGreevy from UCSD today for the seminar today, and welcome to everybody. Although it is a little late in the night, I'm happy that you have been able to join. And today he will talk us about his new approach for understanding many body systems using entanglement bootstrap. So over to you, John.
Okay, great. Thanks, Ian. So thanks for having me. Thanks for staying up late. Yeah, so indeed, this is a talk about recent progress in entanglement bootstrap, which is a sort of quantum state-based approach to quantum field theory and quantum matter. And I want to tell you about some recent work with Bowen Shi, who's a postdoc with us, who's one of the initiators of this program, and my student Jin Long. And then I hope to devote a large portion of the talk to a sort of preview of so that this part is about topological states, an application of this approach to topological gap states, and then I hope to try to broaden the scope a bit in the latter part of the talk and tell you about an extension of this sort of same perspective that can be applied to conformal field theory in 1+1 dimensions and also 2+1 dimensional gap states with gapless edge. Okay, and that's work in progress also with Bowen and David and Shang Li and Isaac Kim from UC Davis. Okay, so the basic principle of entanglement bootstrap is the following, I guess, goal is maybe a good way to say it. It's the idea that we can understand all of the universal properties of states of matter given just a single wave function, a single representative wave function, and not even the whole wave function, just the reduced density matrix of a local region. So the region, so here I've drawn a picture of a ball, I'll call it B, and imagine that the state that we're talking about is living on Hilbert space, which is a tensor product over sites in space. Here I've drawn it in 2 dimensions. It could be other number of dimensions, and it's ideally each of the sites hosts some finite dimensional Hilbert space. And I guess it's good to keep in mind the picture that the state we're talking about is the ground state of some local Hamiltonian, though I won't actually introduce a Hamiltonian. Okay, and so so the region that we're talking about should be well, not too small compared to the lattice spacing, and so the claim is it's a kind of bold claim that all of the universal data about the state of matter that the state represents is encoded in just this small density matrix. And so there's various evidence for this claim from many different points of view. And so let me list a few of them. So one of them is the perhaps familiar fact that from entanglement entropy of a ball in conformal field theory in 2 or 3 or 4 space-time dimensions, we can extract these RG monotones, like the central charge of the Virasoro algebra, the F coefficient in 2+1 dimensions, or the A coefficient in 3+1 dimensions. So these are universal properties labeling the conformal field theory, which you can extract from just the entropy of a round ball or interval in the case of 1+1 dimensions. Another very different example is in topological states, say in 2+1 dimensions. There's this quantity called the topological entanglement entropy. One way to see that is one way to extract that quantity is the term in the entanglement entropy of just a ball subleading to the area law, right? So there's an area law term whose coefficient is non-universal, but then there's this universal subleading term, which in the case of 2-dimensional gap states turns out to count the total quantum dimension of the anyons in the associated topological order. And so another way to extract it is this kind of partition of an annulus by taking various differences. Okay, so a third example, more recent example, also due to Isaac and Bowen and collaborators, is this concept of the modular commutator. So the modular commutator, one way to think about it is the linear response of the entanglement of, say, AB to a modular flow by BC. Modular flow just means evolve using the entanglement Hamiltonian, using the log of the density matrix as the Hamiltonian. And so this is an entanglement measure, or some measure of entanglement, which is, how to say, it's a deeper, sort of higher level measure of entanglement than just entanglement entropies, right? Because it depends not only on the spectrum of the reduced density matrix, but actually the structure of the reduced density matrix as an operator. And these folks showed that that this quantity computes the chiral central charge, either in 2 plus 1d or 1 plus 1d. So the number of left moving modes minus the number of right moving modes. Okay, and there's a generalization of this in the case of a state with U1 symmetry, which can compute the Hall conductance, famously universal property of a gap phase in 2 plus 1 dimensions. And then more generally, I guess, all of these are sort of building up to this entanglement bootstrap program, which has been applied so far mainly to the case of gap states in 2 plus 1 dimensions, where it's been used as I'll review to extract the information about the spectrum of anyons. So the list of anyons, their quantum dimensions, their fusion rules, and indeed their braiding properties also, just starting from a single representative wave function. Okay, so a slightly less ambitious goal, which is, I guess, where we've been until recently, is the following. So in 2 plus 1 dimensions, we expect that all of the universal properties of a topological phase are encoded in a topological field theory. Right, a topological field theory is like it's like a framework for encoding that universal data, and there's some set of information needed that we need to input to the topological field theory to specify it, like this list of anyons and their fusion rules. So one a sort of narrow perspective on the program is to figure out how to fill in that data just from a single wave function. And that we mostly know how to do by now. But I guess more generally, in, say, away from 2 dimensions, or if there are boundaries of various kinds, it's less clear even what the framework is for encoding all of the universal data in the state of matter. And we think it's some kind of topological field theory. It's not entirely clear in 3 dimensions what all the data is needed to specify the topological field theory. And so another larger aspect of the program is to figure out what that data is. Okay, but even if we say that the goal is just to extract the topological field theory data from the wave function, there's an apparent obstacle, which is that the way, certainly in high energy physics, the way we usually think about topological field theory is as a machine where the input is some interesting manifold and the output is some kind of invariant, right? Some quantity that's a integer or some other topological invariant of the manifold and of the state. But I've just told you that we're only allowing ourselves the density matrix on a ball, right, on this very topologically trivial region. How can we access all this other information about the topological field theory from this point of view? Okay, so I'd like to spend the first part of the talk partly answering that question. So I guess first I'll introduce what I mean by entanglement bootstrap in this case, in the case of liquid topological order. So by topological order, I mean some state of matter, gap phase of matter, with this stable ground state degeneracy. So that means that the stable there means that there's no local operator that takes one ground state to another. Rather, they're related by some non-local operators, and therefore the ground state degeneracy depends on the topology of space. And by liquid, I just mean that the ground state degeneracy depends only on the topology and not on the geometry. So that's just to rule out fractons. Yes, please.
I guess I mean, I have a very silly, naive question. Why do we expect that one should be able to extract so much information from a single state? Like, that doesn't seem to make sense.
Yeah, right. I agree. I'm glad that you find this statement surprising. Yeah. So right, I guess my best answer to that question is, here's some evidence that we can, this is at least some set of universal information about these states of matter that can be extracted from the density matrix of a ball. And I guess you could say it's a hope, right? It's a, I guess, I think the best word is principle. that, you know, principle in physics is something where we don't know how to prove it, but, you know, we've seen that it's true often, and it seems to be a good guide for making further progress. So
Well, I mean,
that's, yeah. Mhm.
So the state in general has to be a special state, or I mean, you probably can't just take any state and.
Great. Yeah, so that's a great question. So indeed, my assumption here is that the state that we're starting with is a representative of some phase of matter or some critical state.
Okay. Thank you.
And so, right, indeed, you could imagine, you know, I just take some totally random state in the Hilbert space. I don't really know what to do with that, right? But so the perspective I'm going to take is that so states of matter fall into classes. Right. So the first class that I'm going to talk about is 2 + 1 dimensional topological states. And in that case, we'll be able to identify sharp local conditions that tell us that whether or not a given wave function falls into that class. And actually, so in general, that's really what I mean. That you know, for any class of states, like say 1 + 1 dimensional CFT, we'll be able to identify a sharp local condition on the state that tells us whether or not the state is indeed the ground state of a CFT.
Okay, thanks.
And yeah, and so right, so maybe, yeah, just to give a slightly, your question is a good opportunity for me to give a broader perspective on what I'm trying to do. You know, for other classes of states, I don't know yet how to characterize them, right? So I don't know, for like states in the middle of the spectrum, maybe they can be classified in various ways. I don't know I don't know what demands to place on the state yet. But okay, but I'll show you 3 examples. Well, yeah, roughly slightly more than three classes of states where I can, you know, characterize what I mean by representative. Great, yeah, thanks for the question. Please do ask questions and make comments. That'll make it more fun. Okay, so yeah, so then I want to spend a little while explaining a method within this gapped entanglement bootstrap to overcome this obstacle I mentioned about how to make more interesting manifolds than just the ball. And that goes by the name of Kirby's torus trick, which is a trick from differential topology. And then we'll use that idea to understand the braiding of topological excitations in such states. In particular, we'll use it to understand this notion of braiding non-degeneracy, which is an axiom of topological field theory. It's the idea that any topological excitation can be detected by some other topological excitation. So by topological excitation here, I just mean some excitation that can't be created locally. So if it's a particle in 2 + 1 dimensions, that's an anion. And yeah, so this braiding non-degeneracy is the idea that any anion or any topological excitation braids non-trivially with some other topological excitation. And that's something that we can prove within this framework. Okay, and the way we'll prove it is by introducing this notion of a pairing manifold, it's a manifold with some extra structure, which in the simplest example where of braiding of anions in 2 + 1 dimensions, it's just a torus. So it's some generalization of the way in which the torus is used in the braiding of anions. Okay, and then I'll try to convince you that this notion of pairing manifolds is a fruitful concept. It leads to things like Verlinde formulae, and it'll allow us to extract generalized symmetries just from the single wave function. So that's another set of universal data that we can extract from just the wave function on a ball. And then, so then we'll try to move on to gapless states. All right, so indeed, the first question we have to answer is, if someone hands us a wave function, and sort of say the reduced density matrix on a ball, how do we know that it's a representative of some liquid topologically ordered ground state? The principle that we're starting with, that all the universal data is in there, implies that there should be some local condition that we can use to check whether or not this is the case. And so here's the answer to this question that Bowen and Isaac Kim and Kotaro Kato gave, which is, it's the following simple conditions on the entropy. So just take a ball and divide it into its interior and its thickened boundary, and the condition that will impose, so there are two axioms which are called A0 and A1. The conditions that will impose are that this combination of entropies vanishes, and that this combination of entropies vanishes. And we want this to be true on any disk whose radius is a few lattice where sigma is the given density matrix. In fact, if this condition is true for small disks, the same condition is true for actually any regions with the same topology. So any decomposition of a contractible region into its interior and its thickened boundary, or its interior and its thickened boundary into two parts. If this is true for small regions, it's true for any region with that topology. So let me give you some intuition for what these conditions say. So A0, the condition that this vanishes, is itself an area law for round balls, and that's just because, you know, think of this region where the thickened boundary is a thin shell. Then it says that the entropy of C, which is the interior, is the entropy of B minus the entropy of the whole thing. But then the entropy of BC is positive, and so this is bounded above by the entropy of the boundary region. So hence it's an area law. Combining A0 and A1 actually implies an area law for regions of arbitrary shape and size. And it implies that the subleading term is indeed independent of the shape and size. Okay, and so the most important consequence of these axioms is that even though they're local conditions, they imply statements about arbitrary regions outside the ball. So in particular, A0 implies that the mutual information between the interior of the ball and a region A, which is anywhere outside the ball, vanishes exactly. And similarly, A1 implies that ABC, where C is again the interior of the ball and A is any region outside, form a Markov chain. That is, this conditional mutual information between them exactly vanishes. So yeah, so ABC, so any three regions shaped like this, where B is a buffer between A and C, form a quantum Markov chain. Okay, so now some of you may
sorry, I mean,
yeah,
I just this BCD that you drew for A1 is not exactly this Markov chain like thing where B shares boundary with A and C, but otherwise A and C do not share boundary. So
right. So hold on. So notice that D does not appear here, right?
Yes.
So A is something which is an arbitrary other region. For example, it could be something that's attached to B here, right? So the idea is that if delta BCD is 0, it implies that the conditional mutual information between C and A given B vanishes. Right. So so you see if I attach A to maybe okay, I think I can draw it. Right. So here's C, here's D, here's B. So A is some region here.
Oh, okay.
Right. So the statement is that delta BCD equals 0 implies, using strong subadditivity, that the conditional mutual information between A and C given B is 0. Right. So if we can redraw this, up to topology, it looks like this. Right, up to homotopy.
Just asking, is this like you could say that instead of A1, you could, if you say Markov chain, will it be can you replace A1 by this quantum Markov chain of?
Well, right. So indeed, so A1 implies that these things are quantum Markov chains. The advantage of phrasing it in terms of A1 is that A1 is a local condition. A1 is a condition just on a ball. It's really quite subtle and nice. So whereas saying that arbitrary regions that are separated by a buffer are a Markov chain is not a condition that you can check locally, right? Because you have to check every three regions.
Oh, okay, I see. So
so in that sense, A1 is a very compact and powerful assumption.
But couldn't you say you have three concentric, two concentric rings and ABC? You can think of that way.
concentric rings. I'm not sure. There may be other equivalent starting points. But yeah, this one turns out to be very nice, I guess maybe is the most useful statement I can make.
Yeah, because quantum Markov chain is interesting because it has been probably as a proof that these are the only states that can saturate the strong subadditivity. So you are saying that somehow this representative ground state will saturate the strong subadditivity because if and only if statement that only such quantum Markov chains can saturate strong subadditivity. So that sort of makes it very unique. So in some sense that that if you take three regions of a particular kind, then you should always saturate the strong subadditivity.
That's right. So I guess, yeah, so there are two things I have to say about this. One is that it implies lots of wonderful things about the state. In particular, the usually very difficult problem of the usual difficult quantum marginal problem is actually solvable. In particular, if I give you a state rho AB and a state rho BC that agree on B, in general, you have no way to know whether or not there exists a rho ABC, which is consistent with those marginals. But if you know that it's a quantum Markov chain, then there's a unique rho ABC, which is just the maximum entropy state consistent with those marginals. So in fact, that statement is the main engine of progress here. So indeed, so it's a powerful and wonderful statement about the state. On the other hand, you might worry that this is too strong an assumption, right? Certainly, it's not true that if I hand you a ground state of some gapped Hamiltonian somewhere in the middle of the phase, it's not true that it'll exactly satisfy these two conditions. Rather, we expect that these two conditions are a property of the fixed point of the normalization group. So another way to see that it's too strong is this fact that just the ordinary mutual information between A and C vanish. So if A and C are separated by a buffer, then this condition implies that their mutual information vanishes. That means that the correlation length is 0, right? Because the mutual information bounds correlations between operators supported in A and operators supported in B. And so indeed, this A0 exactly implies that the correlation length is 0, or at least smaller than any of the balls that we're considering. And that's it's a property of the normalization group fixed points. So the actual picture that we have is that if someone hands you a state in the middle of a phase, the axioms will only be approximately satisfied. But if they're only violated a little bit, in fact, we think that there's a threshold for how much they can be violated by, such that if you coarse grain, if you look at larger regions, the axioms become better and better satisfied. So that as an asymptotic statement, the axioms will be true. So if you coarse grain enough, the axioms will be true.
Can I ask something here?
Go ahead. Yeah, please.
Is there some kind of, like, we know that, as you mentioned before, that this P theorem and all this F theorem. But is there some kind of monotonic quantity that involves a multi-party entanglement? Like some of this, like A0, A1 or something of that kind, that will something monotonic? Is it known? That
monotonic under RG.
Which is under RG, yes. Monotonic under RG.
Well, okay, yeah, I'll talk a bit later about C functions in the case of gapless states. In the case of gap states, I guess our understanding mostly is about the fixed points at the moment. And part of the reason is that I guess the fixed points that we're studying here are infrared fixed points, right, with no relevant operators. So it's tempting to only think about the endpoints, and then there's no question of perturbing it by a relevant operator and going somewhere else, right? So the list of anyons and whatever the other data is just, that's what you get, and there's nowhere else to go. In this case, it's sort of the end of the flow. But indeed, it might be interesting to ask about starting with some state that does have relevant perturbations about what has to decrease as you go to such a state. But I don't know. Interesting question. Okay. Yeah, so indeed, so in the discussion that follows, I'm going to assume the exact axioms The version of the theory where the axioms are only approximate, the sort of robust entanglement bootstrap, is something that remains to be worked out. It's a interesting problem. Okay, so having figured out how we identify whether a state is of the right kind, how do we extract the universal information? And so in the case of gap states, a very important idea is this thing called information convex set, which I'll talk about a lot in what follows. And it's a machine that associates to each region of space. So consider a region X, which for now we'll take it to be a subset of the ball in which our density matrix is defined. So the ball B is some is here, and X is some region like an annulus, and it's a convex set of density matrices. It's the set of density matrices which are locally indistinguishable from the given reference state. So by locally indistinguishable, what I mean is draw a little ball contained in X, and given some density matrix on X, compare it in that ball to the reference state which lives on the bigger region, to the reference state sigma. And if it's the same for every such ball that's contained in X, or some slight thickening of X, then it's said to be an element of the information convex set. Okay, so this is some set of density matrices. It's a convex set just because if you add two density matrices satisfying this condition, you get another one. And it's an interesting thing because of this condition that they're only locally indistinguishable. So there can be states in the information convex set of, say, this annulus, which are, so everywhere on the annulus, they're identical to the, locally they're identical to the vacuum. But outside the annulus, there can be all kinds of crazy stuff going on. In particular, there can be an anion in the hole of this annulus which is created by a string operator connected to its antiparticle outside the hole of the annulus. Now, this string operator in a top, the thing that creates an anion, it creates an excitation only at the endpoints, right? The string has to be there. That's the sense in which the anion can't be created locally. But where the string goes doesn't matter. You create the same state if you put the string somewhere else. It's topological. And that means that the state on the annulus here locally is the same, because any choice of little ball here, I can make it so that the string doesn't touch it. I can move the string so that it doesn't touch any ball inside the annulus. Nevertheless, the global state is necessarily different. It knows about the anion inside the hole. Okay, so the axioms of A0 and A1 imply that this information convex set is a topological invariant. In particular, it's unchanged by smooth deformations of X. And by unchanged, what I mean is that entropy differences between density matrices are the same and fidelities are the same. And of course, the structure as a set, as a convex set, is the same. And there's a heuristic argument due to Kitaev and Preskel that it should be insensitive not only also to small changes of the reference state within the phase. Okay, so yeah, so the idea is information convex set of a round annulus is the same as the information convex set of a mushed up annulus. And okay, so the structure of this convex set for various choices of X is a way to extract the universal data. So a few first steps. So if the local Hilbert space is finite dimensional, the information convex set is a finite dimensional compact convex set, and such a set is specified by its extreme points. Essentially, they come in two forms. It can be a simplex, where the extreme points are isolated, like the tips of a triangle, vertices of a triangle, or indeed a simplex. Or it could be like the block ball, like the set of density matrices on a qubit, where the extreme points are, come in this continuous family, the block sphere. Like pure states are the extreme points of that convex set. Okay, first result is that the information convex set of a ball only contains the reduced density matrix of the reference state. So that, I won't go through the argument carefully, but if you choose the region to be topologically trivial, you don't learn anything. But if you choose so let's think about two dimensions. If you choose the region to be an annulus, then the information convex set is indeed a simplex. It looks like this. And so the extreme points are isolated and in fact orthogonal with respect to this inner product. And we can associate the extreme points of the information convex set of the annulus with anion types, right? So, and the picture is basically what I explained already, that if I make a state by inserting an anion into the middle of the annulus, the reduced density matrix of the annulus is one of these extreme points. Okay, so from this density matrix, we can extract various information, in particular the quantum dimension of the anion. Quantum dimension is, what happens if you fuse the anion with itself arbitrarily many times. How does the Hilbert space grow? That's determined by the entropy of that density matrix minus the entropy of the reduced density matrix of the reference state. That's the state associated with the trivial excitation. If instead I study the information convex set of the two-hole disk, that produces fusion spaces of those anions. And these two definitions are consistent with each other in that the quantum dimension can be shown to solve this equation. Okay, and also we can extract the topological entanglement entropy as a conditional mutual information. Okay, maybe that's not too surprising. Okay, so the same axioms, roughly the same axioms apply in any dimension. So in 3 dimensions, again, we just take a decomposition of a ball into its thickened boundary and its interior in 2 ways, and we can make the same assumptions. And the basic results that the information convex set is a topological invariant generalize. But the story about the excitations is much more interesting, because you could ask what generalizes the annulus for classifying topological excitations. And I guess immediately you could think of at least 2. One is you could think about the sphere shell, inside of which you could stick a particle. And indeed, the information convex set of the sphere shell classifies particle excitations. Or you could think about a solid torus, which looks like this, which instead detects loop excitations, right? So here, this red thing here is an excitation, which is a closed loop. The shaded region in here is like a membrane operator, and analogous to this string, which itself doesn't create excitations, but when it has a boundary, it creates excitations. And so the information convex set of the solid torus detects such loop excitations. And in fact, there are many new possibilities. The torus shell detects linked loop excitations. The genus 2 handle body detects these kinds of graph excitations. And more generally, you can think about the information convex set of the complement of an arbitrary knot or link, which detects excitations that have the topology of that knot or link. Okay, so this is something that we spent a while thinking about, and there's quite an interesting zoo of classes of excitations, which are.
Can I ask something here? So
yeah, please.
Since you mentioned this knot, so this density matrices will be different for each different knot. Is there some by construction that your density matrices you said are distinct points and from convex set. So therefore, it's that for every knot you will have a distinct density matrix in this context.
Well, not only that, right? Actually, so for any knot you get an information convex set, right? So the information convex set of the knot itself actually is trivial, because you can. Well, I actually didn't explain this yet, but the information convex set is invariant under regular homotopy. So if I deform the region not only through the deformations are allowed to intersect themselves, actually, as I'll explain. But the information convex set of the complement of the knot is a non-trivial topological invariant, actually. And so it's actually not just one density matrix for each knot, but a set of density matrices for each dot, for each state. Indeed. And in fact, we studied some examples where we could show that those information convex sets can be quite non-trivial. In particular, they can store quantum information. So in this example of the S3 quantum double, there's an example of a knot excitation that's non-abelian, right? In the sense that it's in the same way that 2 non-abelian anions, if you stick them together, there's some Hilbert space, some bigger than one-dimensional Hilbert space. This knot excitation can store quantum information. It has a bigger than one-dimensional Hilbert space. So indeed, there's kind of a bewildering array of possible topological excitations for any 3-dimensional topological order. So let me.
Excuse me.
Yeah, please.
If you can associate invariants to knot complements, do you get hyperbolic invariants or something like that?
That's a great question. Yeah, that's a great question. Actually, so far we've only studied torus knots and satellite knots
Oh,
explicitly, but the answer is yes. The answer is yeah, absolutely yes. And yeah, we spend a lot of time wondering whether there are, you know, new invariants that people haven't thought about
yes,
from
that
other
was my
points of view.
question.
Indeed, and I don't know the answer yet. So so it depends on what's, so we get an invariant for each state, right? For each topological order.
Okay.
And the examples that we've studied so far in detail are simple states like the quantum double model for some discrete group. And in that case, the invariants we get are actually are familiar ones, like coloring, like counting the number of ways of coloring the knot.
Yeah, that's okay. I mean, but you will probably get new invariants.
Indeed. And so whether or not you get new invariants depends on the question of what are the possible topological orders in 3 dimensions, in 3+1 dimensions.
Okay.
And the answer to that question is it's actually not so clear. Yeah, so I think it's a very interesting question.
Okay. Thanks.
Yeah, great.
Yeah.
Uh-huh.
So just to make sure that I understand. So for each of this complements of the knots, you would get different density matrices depending on what kind of excitations you have
Right.
inside the knots, right? In
Exactly.
that are threading through the knots. And
Exactly.
Okay, so that will detect the kind of all the different with different knots. You will be able to define different kind of fusions and all that. So that's the idea that you are trying to essentially bring out in this.
That's right. That's right. And the information convex set of each of these things is itself an invariant of the knot. So
it's an invariant of the knot by itself.
So if you find for two knots, if you find some topological order, so two putatively different knots, if you find some state where the information convex set of this one is different from the information convex set of this one, it means that they're distinct. It means that there's no regular homotopy that takes one to the other. There's no isotopy that takes one to the other. Sorry, yeah, I said the wrong word, isotopy.
Mm-hmm.
Yeah, so in that sense, it's a not invariant.
Mm-hmm.
Okay, so I hope I've conveyed that there's a sort of bewildering array of regions that we can consider, and each one has its own information convex set. So to help put some order to that space of possibilities, it's useful to divide regions into 2 classes. And those 2 classes are associated to which class a region falls into says which kind of information is stored in its information convex set, whether it's classical information or only classical information or actual quantum information. And the distinction is a simple simple topological property of the region, which is whether or not it's sectorizable. So a region is said to be sectorizable if you can cut it into 2 parts, L and R, each of which can be extended to the whole region. So here's a picture. An annulus is sectorizable because I can divide it into L and R, each of which is again an annulus, each of which can be extended by adding little balls back to the original region. And the theorem is that if a region is sectorizable, its information convex set is a simplex. So if the region looks like this, the information convex set looks like this. And the extreme points label independent excitations, which we can think about as anion types. And this is classical information from the very definition, because the data about the state of the whole system, the whole region, is encoded both in L and in R. So in that sense, it's information that can be copied. So it's purely classical information. Okay, I'm not gonna give the theorem, give the proof of this theorem, but the alternative, if a region is not sectorizable, then its information convex set can encode quantum information. So an example of a non-sectorizable region is the 2-hole disk. So the 2-hole disk, you can't divide into 2 parts, each of which is again a 2-hole disk. And in that case, there's quantum information. And so more specifically, here's the structure theorem. The information convex set of an arbitrary region has the following structure. It's the convex hull. So that's what I mean by this plus sign here, of a collection of convex sets, each of which is associated with a particular state of the thickened boundary of the region. So by d omega here, I mean the thickened boundary in the case of this 3-hole disk here, 2-hole disk, it's these 3 annuli, each of which is always sectorizable and therefore has some set of labels if I pick a set of labels of the thickened boundary, that's what A is, then the information convex set, the resulting information convex set is the state space of some Hilbert space. Some Hilbert space V sub A, it carries the labels of the thickened boundary, and it's some finite dimensional Hilbert space whose dimension is an invariant of both the region and the topological order. Okay, so this is what I mean by a fusion space. And so for example, the three-hull disk, if I pick A, B, and C to be the anion types in each of the holes, is associated with a fusion space whose dimension is NABC. I associate it with the number of fusion channels from A, B to C. Okay, maybe I'll skip this definition. All right, so a key tool in all of these results I've mentioned is this idea of merging, which as I said before, in general, the quantum marginal problem is impossible. But if we know that the state is a quantum Markov chain, then given a state on AB and a state on BC, I can find a state on ABC. And moreover, these folks showed that if the state on AB is an element of the information convex set of AB, and the state on BC is an element of the information convex set of BC, then there's a state in the information convex set of ABC, which is the result of merging them, which is really, it's very simple. It's just the maximum entropy state consistent with the marginals. Okay, as a sample application of this technique, we have this so-called associativity theorem, which is a statement about if we merge two regions along a whole boundary component, so there's no boundary left, then the fusion dimensions are related by this convolution. And the reason it's called associativity theorem is this application in two dimensions. So if I merge this two-hole disk with this two-hole disk, I get some, this has some fusion dimension, this has some fusion dimension. The end result has this fusion dimension. I get the same answer as if I merge them in this order, and that implies this associativity theorem for the fusion dimensions, which in the case of two dimensions has the very important consequence that I can stop once I know the story for the two-hole disk. I don't have to keep thinking about, I don't get new independent information from disks with more holes. Okay. All right, how am I doing on time? Oh wow. Okay, so maybe I'm gonna very telegraphically convey to you the idea of how we study braiding. Maybe I won't go into so much detail, but the idea is, starting from the state on the ball to make a state on a closed manifold. And Bowen likes to compare the state on the ball to like a seed, and this process of building the state in the closed manifold is like growing the plant from the seed. Okay, so the key idea is that we could define the information convex set not only for subregions of the ball, but for immersed regions. So by an immersed region, I mean one that's sort of a double cover. So here's a picture of what I mean by an immersed region. In this region here, I'm using the qubits twice, right? So this in the neighborhood of this region, it's a double cover of the ball. And yeah, so this is the Kirby-Torres trick. The idea is that given an immersion into the ball, we can pull back structure from the ball to our immersed region. And so we're going to pull back the reference state. So a priori, it's not obvious that the information convex set defined this. So yeah, so the idea is in order to define the information convex set, we need to be able to compare a state on the region that we're given with the reference state. And so it's okay if we're comparing the state on the region with the same part of the reference state more than once. And so, okay, it's not obvious that the information convex set defined this way is non-empty or contains a vacuum state. But one thing that's true is that, yeah, this generalized isomorphism theorem holds that if two regions are related by regular homotopy, meaning homotopy through immersions, they have isomorphic information convex sets. So that's what I was saying about the information convex set of a knot is the same as the information convex set of the unknot. Okay, the second step and why it's called the torus trick is this region that I drew, you might recognize as a punctured torus, right? If I take a square with opposite sides identified and cut out a hole, if I can move the identification to make it look like this, which you see is like a disk with two handles attached, which is a punctured torus. And the key thing, which I'm not really gonna, okay, so this So every closed manifold, which has trivial Stiefel-Whitney classes of its tangent bundle, can be, if I puncture it, I can immerse it in the ball. And under some assumptions about the boundary, about the state on the puncture, we can heal the hole and make the closed manifold. Okay, so here's a picture of some ways of healing the hole for some various manifolds, which I won't explain. But so there are various manifolds for which we can construct a reference state. And now the most important application of this so far is this notion of pairing manifold. So a pairing manifold, it's actually a pretty restrictive definition. It's a closed manifold which can be cut in half in two ways. So here's a picture of the torus, which is a pairing manifold. And the idea is we can cut it vertically into two annuli, into X and its complement, or we can cut it horizontally into Y and its complement, which are also annuli. And the key assumption is that the two ways of cutting it, X and Y, have the property that all their intersections are balls, and a few other assumptions about the state. And the idea is, because these regions only intersect in balls, and the information coming set of the ball is just a single state, it means that all of the information in a density matrix on X is hidden from the information about the density matrix on Y, because they only intersect in a ball. So of course they agree. Okay. And okay, the key idea is that information comic sets of X and Y each captures some class of excitation, and the existence of a pairing manifold pairing X and Y will imply that the excitations captured by X are detected remotely by those detected by Y, and vice versa. Okay, so this is my most intimidating slide, whose purpose is to point out that there are many examples of pairing manifolds. So despite the fact that it's a very restrictive definition, there are many non-trivial examples. Okay, so such as the torus, the S2 times S1, connect sums of S2 times S1, various examples in other dimensions. Okay, so given that it's a restrictive definition, there should be some strong consequences. One consequence is that the information comic set of X and its complement are the same, and Y and its complement are the same. And then the most important consequence in words is the statement that the pairing matrix is square. Pairing matrix is a matrix I'll define in just a minute. It says that we can make a basis for the fusion space of the pairing manifold in two ways, either starting from excitations on X or starting from excitations on Y. And the two ways of doing that, they're different bases for the same Hilbert space. One consequence of this is that we can count certain kinds of excitations in terms of the fusion dimensions of the excitations with which they're paired. So it leads to things like this kind of identity relating graph excitations to the fusion dimensions of the ball minus G balls, to these fusion dimensions of clusters of particles. Okay. You might ask, given a region X, what is the region that it's paired with? And the answer is, consider the operator that creates extreme points of the information comic set of X. So in the case of the annulus, that's this string segment here. Make two copies of those to cancel out the excitations. It becomes a closed loop. And the region that's paired with X is a region homotopic to that closed loop. So it's homotopic to the operator that creates a pair of excitations detected by the region. So okay, here's a collection of examples of that statement. Okay, and then the application I want to mention is, so suppose for the moment that X and Y are sectorizable, then we can make a basis for the fusion space of the pairing manifold from extreme points of the information comic set of X. We can make another basis from extreme points of the information comic set of Y, and the unitary matrix that takes one of these bases to the other is the S matrix, is the pairing matrix. And
sorry, can I just ask? Okay, so here it looks like there's the difference from what you were saying before is that there was this knot and looking at just this complement, but here you're looking some sort of a linked knot, like two knots kind of linked to each other, and you're doing something on one knot and trying to detect it from the other. So if I want to put it in some other way, is this another way of phrasing it? Or
okay, there's something I need to slightly correct about that, which is that these two excitations they're actually linked in space-time.
Mm-hmm.
Right. So the simplest case is when the two excitations are just particles. right? So let's think about the case of T2. Yeah, so the case where the Perry manifold is the 2 torus, right? So X and Y is each of X and Y is an annulus. So like in this picture here, each of X and Y is an annulus. So that each one detects particles. And the thing I'm trying to describe is the braiding between those particles. And so the braiding there is braiding in space-time, not just in space. But nevertheless, I'm detecting it just by thinking about a state on a fixed spatial manifold, which is this torus. And yeah, so the way in which this makes contact with previous constructions of the S matrix is this state is a minimally entangled state along X, and this state is a minimally entangled state along Y. And these folks use that perspective to define the S matrix for the topological order on T2. Yeah, so it's a generalization of this perspective on the S matrix. Right. So from the point of view of space, it's maybe not so obvious that, well, I don't know.
It's more like an overlap between two states, the way you're defining this.
That's the way we're defining. That's right. Just as the overlap between two states. Exactly.
Yeah, so but what do you mean by something is a minimally entangled state along X?
Yeah, right. So indeed, so I guess here I'm referring to this work. It's so if I put some state with topological order on the torus, some Hamiltonian with topological order on the torus, there's a ground state degeneracy. Right, there's a collection of ground states, and how do we organize them? Well, one way to choose a basis for them is to, well, and actually this is sort of a practical thing actually, because if you're constructing those states, like say by DMRG, if that's how you're finding the states, it automatically finds the states which have minimal entanglement in the direction of your in which you're decomposing the system. And yeah, so I really just mean literally you can choose a basis of the states which minimizes the entanglement along some cut, right? Say along the X direction. And yeah, so these folks showed that if I just look at the overlap between those two different bases for the ground states, it's the S matrix of the anyons. And so that's the sort of, that's how we make contact with familiar definitions of the S matrix. Actually, we know how to make a more direct relationship to space-time braiding of the particles by thinking about acting with combinations of string operators, and show that this definition agrees. But that takes a little more explaining. Okay, good. So maybe I'll just quickly mention, if one of the regions is not sectorizable, then the story is a little more complicated because I need to specify a state of the fusion space of the region and a state of the fusion space of its complement. And that's why I get this square in order to specify a state of the whole fusion space of the Perry manifold. And so the S matrix actually is this more complicated object that has various other indices hanging out of it. But yeah, but amazingly, people actually arrived at such a definition independently from a different point of view. So this is the right notion of S matrix. Okay, so we can use the same point of view to identify generalized symmetry algebra, which let me just briefly mention. We can define an algebra of flexible operators, which are defined by some condition that essentially you can find a representative of the operator on any subregion of the region, which is obtained by removing parts of the region or doing deformation retraction. And the set of operators is an algebra, which moreover has a basis associated with extreme points of the information convex set. So it's sort of a dual of the information convex set. And these operators need not be invertible, and they need not be supported on manifolds. And so that's why I call them generalized symmetry operators. And moreover, if the region participates in a pairing manifold, then there's another basis of these flexible operators which create the extreme points, which are labeled by extreme points of the information convex set of Y.
Sorry, John, this is a little fast actually. So again, what's it? This is. So could you explain this again? This definition of K omega. This set of.
Yeah. So right. So the definition is a little hard to follow, but it's maybe. Sorry, I'm rushing through it because I want to get to the CFT part. But yeah, so
It's okay. We can take some more time. I mean,
okay.
yeah, I mean,
Well, the point I
yeah.
wanted to convey is that there is a definition of a set of operators which matches our intuition that there should be a set of in the case of 2 + 1 dimensional topological, there should be a set of closed string operators, which you should think of as transporting anions around that string, whose algebra should encode, should know about the topological order. And so yeah, so the point of this here is that we've found a definition that that matches that intuition. And yeah, the key demand is that right. So there's this sort of weaker notion of operator equivalence, which we write with a double twiddle, which is 2 operators are equivalent in the sense if when acting on any element of the information convex set of the region, they give the same answer. And the idea is that an operator is you could call it flexible if you can find a representative in this sense, you can find an equivalent operator in this sense whose support can be moved around sort of arbitrarily while preserving the topology. So so here's an example. So here, suppose we're thinking about this 2-hole disk. This is an operator. This is an example of the support that the operator could have, right? It's a thing that moves around these 3 particles in a correlated way. And the operator is flexible if I can find a representative for any such region. Okay, so that's
so basically it's an idea is very similar to this idea of this stabilizer codes where you take operators and you add stabilizers to them, they can move around. And
exactly. So indeed, if we were studying a stabilizer code, we would have explicit representatives of these string operators in terms of products of z's and products of x's along various loops. Indeed, so if the state we're studying is the ground state of such a stabilizer code, these operators are the same operators. However, the nice thing is that we've defined those operators without knowing that we're starting with a stabilizer code, right? So it's a just given the ground state that satisfies the axioms.
Mm-hmm.
Okay, so if the region participates in a pairing manifold, there's a second basis for this operator algebra, labeled by extreme points of the information convex set of the dual region of if the operator algebra of Y has a basis labeled by extreme points of X. And we can define structure constants of the algebra in this basis. And very interestingly, it's not hard to show, just based on what we've done so far, that those structure constants satisfy a Verlinde formula. Namely, they're related to the S matrix by this Verlinde-like formula. And well, I guess one interesting thing is, in general, these numbers are not integers, but in some cases we can relate them to a fusion dimension, in which case they have to be positive integers. Okay. I'm going to skip these open questions. Good. So now let's back up and broaden our perspective a little bit. So I said that the big goal is to understand universal properties starting from just a single representative state on a ball. And yeah, but so far I've only talked about one particular class of states where I assume that it's this liquid topological order fixed point. So if this is possible, if it really is possible to understand all the universal properties from just the reduced density matrix on a ball, then there must exist some criteria on the state that characterize each family of phases. So topological field theory, as I've described, conformal field theory, fractons, whatever class of states you pick. So let's try to ask, what is the analogous condition for CFT? Okay, so the starting point here is, so let's assume that our state is a CFT ground state and see what we know about it and what can be a characteristic of it. So one thing we know is that the entanglement Hamiltonian of an interval, so the log of the reduced density matrix of a single interval A, is related to the energy density. It's related to the Hamiltonian density by it's a local operator, which is this integral over the region of some particular function. That function takes this form if x1 and x2 are the endpoints of the interval. And so this function it's just a locally quadratic function. And my amazing student David observed that quadratic functions, satisfy various relations. So in particular, there's a combination of these functions you can take, which produces a constant. Actually better to say which produces 0, which cancels out. I guess actually, sorry, this equation is not quite true. There's an additive constant in here that I've left out. There's a term, proportional to the identity operator. And so David observed that this combination, so if A, B, C are 3 contiguous regions, like in this picture, x1, x2, x3, x4 are labeled their endpoints, then in terms of the cross ratio, eta of those endpoints, this formula implies that this combination of operators, so this is really just a statement about the corresponding quadratic functions, which are depicted here, they add up to 0, so that all that's left is the constant term. And if you take the expectation value of both sides, you can see that the constant has to be C over 3. C is the total central charge times h of eta, where eta is the cross ratio and h of eta is the binary entropy function, this function here. Okay, so that's a fact about the entanglement Hamiltonians of ground states of CFT. But notice that it's a local condition, right? If I pick 3 contiguous regions that are part of my CFT ground state, I can check whether or not this operator identity is true. Now, as a formal statement about CFT, it's just a fact. We can ask if I have some quantum critical state, like a wave function on the lattice made from the critical point of some Hamiltonian, is this identity true? Actually, the thing that's in that case, it's a little hard to check the operator identity because generally the reduced density matrix has some kernel, and so its log is not so well defined. It's better if we act on the state itself because that removes the kernel. So in a lattice model, the equation that's sort of more robust is the sort of vector form of the equation, so that if I act with the left-hand side on the state, it's the same as acting with the right-hand side on the state. It's a slightly weaker, but still actually very powerful statement. And so here's a plot of the variance of k delta. So this says that k delta acting on the state is just a number, so it has 0 variance in the state. And so in the critical transfer field Ising model, as a function of the system size, the error is very tiny. So it's a true statement, even numerically in a lattice model in finite size. Okay, and so we'd like to propose that this condition, actually, even the vector form of it, is the analog of A0 and A1 for a CFT. It's a locally checkable condition that characterizes the ground state of a CFT. So it should be true for any 3 contiguous intervals that this combination of entanglement Hamiltonians is a number when acting on this state. So that is k delta acting on the state is proportional to the state again. So I said all universal data can be encoded in this local density matrix, but what is the full set of universal data? In general, we don't know, but a sort of hack to show that this is true is if we can reconstruct the whole ground state and reconstruct a parent Hamiltonian from that reduced density matrix. So let's proceed to do that. So first of all, we can reconstruct the ground state if the state satisfies this fixed point equation. Let's consider the operator equation for now, because I can solve this equation. So notice that this equation involves KAB, KBC, so it involves 2 site density matrices, 1 site density matrices, and this 3 site density matrix, the density matrix of the whole ABC. I can solve that equation for KABC in terms of 2 site and 1 site density matrices. So if our fixed point equation is true for every 3 intervals, it means that every 3 interval density matrix is determined by the 2 interval density matrices. It means that I can reconstruct row ABC given row AB and row BC. This generalizes the Petz reconstruction map, which holds in the Markov case, to which it reduces when eta equals 0. So if eta equals 0, this term goes away, and this is just the usual Petz formula. So we can do merging for CFT ground states. So that reconstructs the full ground state from its parts. Now, what about the Hamiltonian? Okay, let's divide up a circle into equally spaced intervals and regard each interval as a site. Okay, so I'm going to use that notation. I'm going to call an interval a site, and I'm going to think of it as it's a site with an infinite dimensional Hilbert space. the density matrix on ABC can be used to reconstruct in this way a lattice Hamiltonian in the following form. So basically the idea is the Hamiltonian is the integral of the Hamiltonian density with coefficient 1. If each of these entanglement Hamiltonians is the Hamiltonian density integrated against one of these locally quadratic functions. But if I add up the locally quadratic functions in this combination, so this is K2, K of 2 sites minus K of 1 site, it becomes a constant. So this blue line is the sum of the coefficients. And so that's the Hamiltonian. You might think, well, this is a formal trick. What does it mean? But actually, if you study it, if you study this combination, the 2-site density matrix minus the 1-site density matrix summed over all the sites, for even a very small quantum critical state. So this is the Heisenberg chain on 8 sites, right? So that's some quantum critical wave function. If I compute the spectrum of the full Hamiltonian, I get the red circles. If I compute the spectrum of this reconstructed Hamiltonian, I get the X's. So it's a formula that actually it's a very robust formula that is exactly true in CFT, but it works even when the local Hilbert space is small. In fact, there's a similar formula for the rest of the conformal generators as well. So for the momentum, for the angular momentum, for the dilatation operator, and for the conformal boost.
Sorry, John, so just one thing confusing. So of course, the CFT Hamiltonian is generically not unique, right? Because so it means that of course for this there will be many possible, I guess. But
That's a great question. Actually, the answer is that there is a correct one, which is this one. So right, so you might worry that the non-uniqueness that you can imagine are there's the additive normalization, of course. So this one is normalized so that the ground state has 0 energy in infinite volume. And then there's the multiplicative normalization, right? But there's a correct multiplicative normalization, which is that you'd like radial quantization to be true, right? You'd like the energy of this. So by the state operator correspondence, the states correspond to primary to scaling operators, and you'd like the energy eigenvalue of the state with dimension delta to be 2 pi delta over L, where L is the radius of the circle. And yeah, so there's actually a prefactor that I didn't put, but which we can figure out, which makes it so that also the multiplicative normalization is correct.
Mm-hmm.
Yeah, so indeed, it's the correct, well, okay, on the lattice model, this formula gives, I'd like to say it's the Hamiltonian on the lattice that's closest to the ideal CFT Hamiltonian.
So this 2-interval density matrix, let's say, can it be arbitrary or not? So this is not probably, should satisfy some further constraints, because you said that for the 3, you can always so there's maybe a stupid question. I mean,
no, that's right. So the 3-site density matrix is determined by the 2-site density matrix and the 1-site density matrix. If the state
does it mean that we can choose them?
Equation. Well,
yeah, but can we choose them arbitrarily or not?
That's a great question. That's a great question. That's a question about what is the space of CFT ground states? Exactly.
Yeah, exactly. Is there any further constraints, or what constraints the choices of this?
Good. So we'll see that actually it is somewhat constrained. In fact, well, yeah. So hold that thought for just a minute.
Okay.
Yeah. Okay. So here's a wonderful surprise that will illuminate the answer to that question. This condition star, this fixed, what I've called the fixed point equation, it's the condition to extremize a simple function of the entropies. So define this function. So for any 3 contiguous intervals ABC, define this function S delta. It's a function of the state. Given the state, it's a number, which is just this difference of entropy. So eta here, think of it as just the geometric cross ratios of the sizes of the intervals. It's a positive function by strong subadditivity. And the condition that if I vary the state, the variation of this quantity is 0, which, yeah, because of the fact that it's made from entanglement Hamiltonians, the variation of any of these S's is of this form under the variation of the state. If I vary the state, I get 0. That gives me this equation star. So that means that there's this simple function, and for which CFT ground states are saddle points. And moreover,
So again, for this particular condition, should ABC be arbitrary all region or any three regions? If you do it for any three regions, it could be sufficient that any other regions will also be true, or that didn't follow.
Well, right. And good point. So right. So here I'm thinking about ABC are three contiguous intervals.
Yeah.
And indeed, you could imagine that there are states for which this extremal condition is true for some intervals, but not for others. Right. So indeed, the condition for a CFT ground state is that it's true for every choice of three intervals.
So we have to choose, like, so for example, you have to choose, like, if it's sufficient to like fix the length and choose it for say continuously for along the varies a B, and you choose A and C. So suppose I choose A, B, C to be like 3, right, on a lattice.
Yeah,
and
yeah.
If it's sufficient to do it like this, or have to then still.
That's a great question, actually. Yeah. So indeed, how many do you have to check before you know that the rest of them will be true?
Before you know the rest would be true. Yes.
I don't know the answer to that. That's a good question. Yeah. Let me tell you the kinds of things we've done. And yeah, that's a great question, actually. But let's think about just a single choice of ABC for now. So the value of the function at the extremum is the central charge times this h of eta over 3, right? Using that identity, just because S is the expectation value of K, right? So if I take the expectation value of the left-hand side, I get just this number. And so it's very reasonable to conjecture that critical points of this function, just meaning critical points as a function of the variation of the state, are in one-to-one correspondence with a normalization group of fixed points. And so here, here's actually, well, okay, let me explain what this picture is. Let's divide up the circle into 4 equal regions. And moreover, rather than thinking about an infinite dimensional Hilbert space for each of these regions, let's suppose that each of them is just a qubit, just a single qubit. So it's a vast truncation of the whole Hilbert space. Each of them is just a qubit. And I'm going to assume that I'm going to look at states which are translation invariant and time reversal invariant for simplicity, and look at this function on the space of 4 qubits, right? So it's I don't know, it's like a six-dimensional space of states, and David did using Newton's method searched for the critical points of this function, and here's what he found. So here are the values of C at the critical points. Here are the forms of the wave function up to some on-site unitary, and here's the identification we can make of these states. So how do we identify what state a critical point is? So one hint is the value of the central charge, right? So here's one, there's only one critical point whose value is around 1/2. And so it's natural to identify that with the Ising critical point. The second thing we can do is, given the extremum of this function, given the state that extremizes this function, we can reconstruct the Hamiltonian using the formula, this K2 minus K1 formula. We can make a Hamiltonian whose ground state it is, and we can study the rest of its spectrum. And so, as I said, it's normalized so that the eigenvalues of this reconstructed Hamiltonian just tell us the dimensions of the operators. So indeed, the spectrum of this state agrees with that of the Ising Hamiltonian on 4 sites. Similarly, around C equals 1, there are 2 states corresponding to C equals 1 CFTs. One is actually the ground state and spectrum of the XX model. Another is the ground state of the Heisenberg model. And then there's some other fixed points. One of them is cat states, which have C equals 0, where there's a ground state degeneracy. There's a state which is where there's another ground state degeneracy, like in a ferromagnet. And then perhaps most interesting, there's a state where here we had 4 sites. There's a ground state degeneracy. Okay, I forget the number. But if you reconstruct that Hamiltonian and study it on larger systems, the ground state degeneracy is equal to the on L sites, it's equal to the Elf-Lucas number, which is the degeneracy of the Fibonacci chain. And then there's the state, this maximum point, which is a perfect tensor state, a state where whichever subsystem you study is maximally entangled. Okay, so some of these can be identified with known conformal field theories. If instead we study, instead of qubits, we study Q-trits, we find more critical points associated with conformal field theories with slightly larger central charge. The ones that don't correspond to conformal field theories are like fail this condition that Ian was asking about. So if we study different regions, or if we vary eta, we get a different answer. So maybe a good way to say it is like these ones that have a ground state degeneracy, actually they would satisfy the fixed point equation for any value of eta. Like this maximum point here, eta doesn't matter. Because these entropies are, they're essentially zero. So there are local criteria. So given a critical point of this function, it's easy to tell whether or not it's a CFT. But
John, in this, sorry, when you increase the number of the dimension of the qubit, make it Q-trait or end it. So when you increase this n, the dimension of the qubit, does the central charge become better, closer to the actual
it does.
value,
that's right. Yes, that's right. It gets closer to the right answer.
To the right answer.
Yeah,
I see.
Yeah, exactly.
So that's interesting. So how much? How many? For example, what should be the good dimension? For example, to get a reasonably good approximation, you think, to be able to simulate?
I don't know. Yeah. So far we've been thinking about, so it's a way to look for CFTs, which, it's very different from any other approach to classifying CFTs, right? We just study all the states on this small Hilbert space and see what we get, right? The exploration, in the case of Q-trits, we haven't finished identifying all of the fixed points. But yeah, so the exhaustive exploration is a little harder to do. But I think if you identify the state, it's not hard to go to bigger system size. So yeah, in the end, I don't know what the best approach is or how big we have to go.
Hi, John.
Sorry.
Yeah, just a question. So does it bootstrap CFTs with only Virasoro, or can there be other symmetries?
Let's see. Well, I guess right. No, these C=1 theories have U1 affine algebras, right? Yeah. So
is there a way to make it bootstrap only?
So I see. You want a condition that imposes not only that there's Virasoro symmetry, but that there's also the extra affine algebra. I don't know. I don't know the answer to that. Maybe. Yeah, I like that question.
And a related question is probably whether, because we are not getting. So, are you getting a continuous central charge? Is it or not? When you get more and more things in between, do you think that?
That's right. So for qubits, we only find these two endpoints of the C=1 line. We only find the XX model and the Heisenberg model. And actually, the Heisenberg model is a little higher. And in fact, if we study, say, the XXZ model, which interpolates between them, this function actually grows continuously from one to the other. So in this approximation on 4 qubits, the ones in between are actually not extrema. They don't satisfy the condition. When we study Q-trits instead, actually, we do find some points in between, but isolated points in between.
Yeah.
I don't entirely understand which ones are allowed and which ones aren't. So, there's generally a sense that to get a state with larger central charge, you need a larger local Hilbert space. But other than that, I don't quite understand which ones appear. Great. Okay, so I'm over time, so let me just advertise the next frontier. which is the case of 2 + 1 dimensional states with gapless boundary. So suppose I have so consider some chiral topological order in 2 + 1 dimensions. If I put it on a cylinder like this, it's really a non-chiral 1 + 1 dimensional CFT in the sense that there's a right mover going this way and a left mover going this way. And therefore, it should satisfy the fixed point equation. I've rewritten the fixed point equation in terms of this quantity delta hat, which is the sort of operator version of the weak monotonicity quantity, and I hat, which is the operator version of the conditional mutual information. It's just the same quantity I talked about before. Okay, so now if I assume that the state on the cylinder satisfies A1 for some regions big compared to the correlation length, and a few other weak assumptions, it actually implies this local fixed point equation for the state near the boundary. So I'm zooming in near this boundary. On a single boundary, if I consider these regions, so A, B, and C touch the boundary, and A prime and C prime are sort of these interior things that shield B from the bulk, then this identity follows. It follows from this 1 + 1 dimensional fact and a few other weak assumptions, including bulk A1. Bulk A1 implies that I can deform the regions in the bulk, right? Like I can make this little bump here, I could deform C prime into A prime or B into A, and it doesn't change this quantity. It really only depends on how the intervals touch the boundary and their topology. So I claim that this is a locally checkable condition for a gapless boundary, or for the conformal field theory on the boundary of a 2 + 1 dimensional bulk, where now the chiral central charge can be non-zero. A remarkable consequence of this is that we can reconstruct the conformal geometry of the boundary. So far, the eta that appeared in my identity was just the geometric cross ratio of the sizes of the intervals. But actually, so here's a sort of reimagining of what we're doing. Given any 3 intervals, just given the state, I can compute delta, which is this combination, and I can compute I, which is the conditional mutual information, and then I can determine C as the solution of this equation. So exactly where this equation comes from will be clear in just a second, but you can see that if I know delta and I can determine C. And then I can determine eta in this way. So where do these come from? The simplest way to think about it is in the case where the state has no bulk and is just 1 + 1 dimensional CFT, then using the known form of the entanglement entropy of an interval, delta, this combination of entropies, is just minus 6c log eta, which is the same as this equation. And the conditional mutual information you can show just by plugging in this formula for the log is minus 6c log 1 minus eta. So if you take this combination of delta and eta, delta and I, this is just eta plus 1 minus eta, which is 1. Okay, so this is a way of extracting the central charge from a state and extracting a cross ratio from the state. So the state knows what the cross ratio of the interval is. It knows the conformal geometry of the boundary, meaning the distances modulo conformal transformations. In the case where there's a gap boundary, the fixed point equation reduces to a boundary version of A1 that was introduced by Bowen and Isaac. In the case where there is a CFT in the case where there's a 2 + 1 dimensional state with a CFT on the boundary, this makes sense. And then finally, it also makes sense even if the edge is some like rough thing. Here I've drawn or Shang drew some bumps, but it can really be, I haven't made any assumptions about some nice geometry of the boundary. And nevertheless, we can extract these cross ratios, and we can prove that the cross ratios computed this way, if the state satisfies the fixed point equation, are the cross ratios of the intervals on a circle. So that is, we can find a map from the boundary of the system to a circle where the boundaries of our regions map to some points on that circle, such that the etas that we compute using this formula are just the geometric cross ratios of those intervals. It's a kind of uniformization map from this, just given the information about the state. The state knows the conformal geometry of the boundary. And then moreover, certain modular flows, which we call good modular flows, of this state produce a new state that still satisfies the fixed point equation. The new state, however, has different etas, and therefore this is a flow on this, deformation of this map phi. from the circle to the circle, it's an element of diff S1. So as a map on phi, it's an element of diff S1, but as an action on the state, it actually is a representation of the Virasoro algebra. So in this way, we can actually extract the Virasoro algebra acting on the boundary CFT just from the state. So yes, so far we've done a bunch of tests of this idea in large systems of P plus IP, where we can use free fermion methods, and it actually seems to work very, very well. So that's the frontier. And then finally, okay, so this is my last slide. The fixed point equation that I described is equivalent to the statement that this function C that I just defined is stationary for all variations of the state that preserve the norm. In the case of 1 plus 1 dimensional relativistic CFT, quantum field theory ground state, not necessarily CFT, for a certain choice of intervals, the C defined this way is the same as the C function defined by Cassini and Huerta. So yeah, in the case when the intervals look like this, where it's two intervals that overlap only a little bit, so that we can think of it as a derivative. This is the C function that Cassini and Huerta defined, and this theorem above shows that C is stationary not just under the variation of couplings, which is something that Cassini and Huerta showed, but under an arbitrary variation of the state. Okay, so there are lots of questions. The most urgent of which to me is clearly there's some relationship between gradient flow on this function and the RG, right? Saddle points of this function are RG fixed points. So clearly, if I move away from a saddle point, it should have something to do with some perturbation of that fixed point. And ideally, we'd like to understand to what extent the Hessian of this function determines the spectrum of operator dimensions of the CFT, and moreover, to what extent do the third derivatives have something to do with the OPE coefficients. So in the Zamolodchikov C function, there's just an equality between the Hessian and the operator dimensions and the third derivatives and the OPE coefficients. This C function is actually not the same as the Zamolodchikov C function, but nevertheless, we can ask how to extract that information. Okay, so the big picture I tried to present is this principle of entanglement bootstrap, that all the universal data is about a state of matter is encoded in density matrix of a ball. So far, we've understood how to implement this principle in the case of liquid bulk topological order, gapped interfaces between topological orders. I didn't say much about 1 plus 1 dimensional CFT, a little bit about 2 plus 1 dimensional chiral states. But of course, there are many other possible classes of states. I mentioned excited states. We can ask about higher dimensional CFT, non-relativistic CFT. Yeah, lots of other crazy things whose answers I don't know yet. Okay, that's the end. Sorry for going over, but thank you for your patience.
Well, thanks a lot for this wonderful talk. Yeah, and yeah, so maybe we can have some more another talk from you at some other point on our channel with some more details of the last part that you mentioned, which was quite fascinating. And
yeah, it's still we're still figuring it out. So I guess that there will be more details in the future.
Yeah. Okay, so now let's take some more questions from the audience. Okay, it is probably pretty late.
Right, yeah, you guys must be tired.
Okay, so thanks for this wonderful talk again. And I will ask for your slides because some of the things were a little,
sure.
We couldn't see, yeah, it was a bit fast. So I'll put a link to it. And so I officially now record the stop, then we can chat a bit. Where is the stop recording button? Oh, I can't find the stop recording somehow. Here it is. Because